The investigation into the loss of Avro Lancaster, Mark III JA914, operational code DXO, is best framed around the confirmed combat loss and the surviving recovery evidence, not around an exact reconstruction of every mechanical and aerodynamic failure. Operating under Number 57 Squadron out of Royal Air Force East Kirkby, the heavy bomber participated in a major night offensive against Berlin. The events bridging the late hours of the 3rd of September and the early hours of the 4th of September 1943 established the baseline for all subsequent forensic recovery efforts. At around midnight, with one account placing the claim at about 0031, the aircraft was reported at about 15,000 feet. The bomber was roughly 25 miles from the primary target area. At this precise juncture, the operational environment shifted from a navigation problem to a critical survival constraint. The loss is generally attributed to a Focke-Wulf 190 night fighter of JG-300, flown by Unteroffizier Fritz Brinkmann, rather than documented in open sources as a fully reconstructed interception sequence. The engagement introduced severe and immediate damage to the British aircraft. The resultant structural and systemic failures forced an irreversible departure from controlled flight. Later local witness accounts provide the main visual description of the final moments, but they should be treated as recollections rather than a formal tracking record. Witnesses reported that the Lancaster swerved violently away from the main interception zone. This maneuver indicates a catastrophic loss of primary flight controls or an immediate attempt to break the engagement under extreme duress. The heavy bomber then entered what observers described as a burning loop. The reported burning loop is best treated as a visual description of a bomber on fire and out of normal control. It may point to severe combat damage or a desperate evasive maneuver, but its evidentiary value remains limited to the visible loss of normal control. The descent from 15,000 feet represented a terminal energy state, culminating in a high-speed impact. The physical endpoint of this descent was the Wünsdorfer See, a local body of water that immediately absorbed the kinetic energy of the crash. The initial evidentiary recovery phase commenced within hours of the impact. The heavy bomber carried a total of 7 crew members for the night mission. According to a later witness account, 2 deceased crew members were found near the Lido on the morning after the crash and buried locally before later transfer by the British. This account provides an important clue to the impact area, but it should not be presented as a formal shoreline search record. However, this initial shoreline search left significant gaps in the historical and forensic record. The secondary phase of the initial recovery involved direct interaction with the submerged wreckage. Local accounts later stated that Soviet personnel recovered 2 more deceased crew members still strapped in their seats from the fuselage. If accurate, that report indicates that some fuselage structure remained recognizable, but it does not by itself prove how much of the main fuselage survived the impact or what extraction method was used. Despite these local accounts, the stronger boundary is the official casualty record. All 7 crew members were killed. 3, Hugh Ivor Jones, H.M. Porteous, and Arthur Sutcliffe, are recorded at Berlin, 1939 to 1945, War Cemetery, while the other 4 crew members are commemorated at the Runnymede Memorial. The local accounts therefore should not be used to state that exactly 3 men were never located. Following the extraction of the 4 crew members, the site transitioned into a dormant state. No further official recovery operations targeted the primary airframe, the engines, or the remaining internal systems. The surviving structural elements of the Lancaster settled completely into the mud of the lakebed. For decades, the main airframe remained unrecovered, but it was not entirely untouched by history. Public accounts report that private divers located the right wing section in 1995, 2 years before the museum-backed recovery in 1997. This massive temporal gap shifted the nature of the site from an active crash investigation to a long-term environmental preservation problem. The central question for future investigators would not be why the aircraft crashed, but what the lake had allowed to survive. The Wünsdorfer See answered that question through 2 practical variables: footprint and depth. The lake covers an area of 400 acres, providing a broad geographical footprint for the initial impact. However, the critical dimension for the forensic survival of the bomber is the depth. The grosser Wünsdorfer See reaches roughly 36 feet at its deepest point, but public recovery accounts place the recovered right wing section in roughly 18 feet of water. This shallow profile left no water column for gradual deceleration, so later recovery expectations had to begin with sudden water impact rather than an intact underwater wreck. When an aircraft hits water at high speed, the destructive load comes from sudden hydrodynamic impact and violent deceleration. The light aluminum alloy structure of the fuselage and outer wing surfaces would have been highly vulnerable, but the public recovery accounts do not provide a detailed debris map or a part-by-part failure analysis. The safer baseline is that the aircraft was destroyed in the crash, while a large right wing section with attached or deformed fuselage material survived in a recoverable state. The shallow lake affected access and preservation, but it should not be used to claim a precise underwater fracture pattern that was never formally documented. The surviving heavy components are best explained through the Lancaster's reinforced wing roots and main undercarriage assemblies, areas built to absorb landing loads and support heavy payloads. During the high-energy fluid impact, these dense steel and reinforced aluminum sections act as heavy projectiles. Under their remaining momentum, the heavier assemblies could continue through the water after the initial hydrodynamic impact and settle into the lake sediment. The lake environment effectively filters the wreckage, destroying the light components while preserving the massive structural cores. The known recovery evidence does not map a debris field across the full lake. What can be said with confidence is narrower. The right wing section, with undercarriage and deformed fuselage material, was found near the middle of the lake at about 18 feet of water. Other major pieces, including the left wing and one engine, were only suspected to remain below the surface in public accounts. The shallow depth made the site accessible to divers, but poor visibility and sediment still kept the wreckage effectively hidden. Understanding this strict division of survival is critical for defining the scope of any recovery mission. The catastrophic fragmentation ensures that a complete, intact airframe does not exist beneath the surface. The recovered section therefore set a practical survival boundary, not a full map of the aircraft beneath the lake. The challenge for future operations would not merely be locating the wreck, but finding a way to extract these isolated, heavy components without causing further damage to the compromised metal. That boundary made the 1995 search a question of diver access, local memory, and recoverable structure. In the spring of 1995, volunteer aviation enthusiasts and hobby underwater archaeologists Carl Friedrich Heide and Rüdiger Snee systematically searched the Wünsdorfer See and located the largely intact right wing near the middle of the lake in about 18 feet of water. On the 29th of September 1997, a Deutsches Technikmuseum-backed recovery lifted the section, with the museum reportedly funding the work at about 25,000 marks, or roughly 10,000 pounds. The objective was not to solve the crash, but to secure physical artifacts for historical preservation. Public accounts describe diver search and a later museum-backed lift, not sonar, magnetometer work, or a formal target triangulation protocol. The case for recovery rested on a combination of historical value and material condition. Freshwater is generally less aggressive than saltwater for many submerged aircraft components, and mud cover can slow oxygen-driven corrosion, but the public accounts for this Lancaster do not provide a full chemical study of the lakebed. The important verified point is narrower. Museum and diving accounts describe the recovered section as in good enough condition to lift, clean, and display. That limited preservation finding made the museum lift plausible but not open-ended. If the bomber had crashed into the ocean, the structural roots would likely have weakened beyond the point of safe recovery after more than half a century. The operation therefore treated the lakebed condition as a narrow recovery window, not as proof that the entire aircraft remained recoverable. The financial investment by the museum was directly tied to this preserved material integrity, aiming to translate the underwater reality into a surface exhibit. The freshwater and mud environment helped preserve enough structure for recovery and display, but only careful handling after lifting could turn the underwater wreckage into a stable museum object. The transition from locating the target to actually moving it presented an entirely new set of physical constraints. The transition from locating the target to moving it now depended on weight, mud, and structural fragility. The physical extraction of the aircraft components from the lakebed introduced strict operational constraints regarding weight and structural fragility. The recovery team had to confront the reality of lifting massive aviation parts that had been buried in dense sediment for over 5 decades. The primary challenge was embedded weight. Water and compacted silt had entered the wing root, spar cavities, and mechanical housings, making the artifact far heavier than its dry factory weight. To safely extract the starboard wing section and the heavy landing gear, the recovery operators had to calculate the required lift capacity while accounting for this immense added mass. If a crane or a series of lift bags applies upward force, assuming only the weight of the aluminum and steel, the equipment will fail, or worse, the sudden resistance will rip the fragile structure apart. The mud creates a powerful suction effect against the lakebed, requiring a slow, controlled breakout force to break the seal without snapping the degraded metal. The initial lift phase is the most dangerous, as the waterlogged structure must tear free from the gripping clay and silt. The undercarriage also had to be tied into the lift so the load passed through the strongest surviving framework. The public record does not provide a full rigging drawing, but it does preserve the broad method. The wing section was made buoyant with airbags, drawn toward the surface and shore, then prepared for the final crane lift with carefully arranged lines. During the first final lift, the load proved heavier than expected, and the lines began to threaten the fragile wing skin. Public accounts report that the piece weighed about 8.5 tons rather than the estimated 6 tons. The team then flushed out water and mud and reinforced the underside with planks before the second attempt succeeded. The verified outcome is therefore not an abstract rule about single-point lifting, but a documented sequence of failed lift, weight reassessment, washout, reinforcement, and successful second lift. That sequence set the practical limit of the operation. Recovery would follow structural viability, not a desire to clear the lakebed. The successful extraction of the right wing section, undercarriage, and deformed fuselage material marked a practical boundary for the 1997 operation. Public accounts show that the lift recovered one large recognizable section rather than the whole aircraft. That outcome should be framed as a limited museum recovery, not as proof that a complete archaeological survey deliberately rejected every other piece of the wreck. The core mechanism driving this decision is partial wreck bias. This concept describes the physical reality that only heavily reinforced structures can survive both a catastrophic high-speed crash and decades of submersion intact enough for single-point recovery. The heavy bomber possessed massive internal strength, focused around the wing roots and the landing gear mounts. These specific components were engineered to handle the intense dynamic loads of flight and ground impact. Because of this inherent strength, these sections endured the explosive surface impact that shattered the rest of the aircraft. When the recovery team evaluated the lakebed, they found that only these robust components retained enough structural cohesion to withstand the stress of a heavy lift operation. The remaining material would have required a different mission: grid mapping, sediment removal, and individual fragment recovery, with little prospect of producing a coherent museum object. The targeted lift therefore set a permanent proof limit. It secured the strongest surviving evidence while accepting that the scattered debris field would not be converted into a complete aircraft record. Once the wing root and landing gear cleared the surface, the underwater phase ended. The operation had succeeded as a targeted lift, not as comprehensive site clearance. The next hazard was atmospheric exposure. The same structure that had survived the lift now had to survive open air. The moment the heavy components of the bomber breached the surface of the lake, the most critical phase of the material preservation began. Removing 54-year-old wreckage from an anaerobic mud environment does not save the artifact. It immediately places it in extreme jeopardy. The recovery team had to secure the extracted starboard wing and undercarriage assembly against the severe consequences of atmospheric shock. This concept defines the rapid, destructive chemical degradation that initiates the second a submerged, waterlogged artifact is pulled into oxygen-rich, dry air. That protected underwater state ended as soon as the wreckage reached open air. The surviving aluminum and steel components were heavily oxidized, structurally compromised, and saturated with moisture. If simply left to dry on the shoreline, the remaining metal would rapidly corrode, the trapped mud would harden and crack the fragile aluminum skin, and the structural integrity of the surviving spar sections would quickly fail. The transition from the lakebed to the surface required immediate stabilization protocols to arrest this accelerated decay. The recovery team had to manage the moisture content, preventing the sudden drying of the corroded layers while preparing the massive components for transport. The wet mud packed inside the internal wing cavities had to be carefully managed, as removing it without proper support could cause the weakened internal ribs to collapse under their own weight. The successful extraction shifted responsibility to the Deutsches Technikmuseum, where the wreckage had to move from shoreline handling into controlled conservation, regulated humidity, temperature management, and corrosion treatment. The conservation process involved carefully cleaning the 54 years of accumulated lake silt from the fragile aluminum surfaces without stripping away the surviving original material. The preserved wing root and undercarriage now serve as a physical record of the 1943 loss, giving the public a scale and violence that photographs alone cannot convey. By arresting the decay, the museum secured the physical legacy of the aircraft, ensuring that the heavy structural anchors remain accessible for public display and historical verification. The surviving wreckage stands as a bounded mechanical record of what the Wünsdorfer Sea allowed to endure.